Once again, I welcome you to the UNU-INWEH public event, the Science Talk. I am your host, Professor Grace Oluwasanya. Those who are joining us for the first time, we are glad you can make it today. Thank you very much. Before presenting our distinguished speaker, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions you may have. Please type your questions or comments in the Q&A chat box. We will pick them up from there when it's time. Thank you again. The topic of today's talk is investing in nature. I really like that. Hashtag investing in nature. The role of wetlands as natural climate solutions. So let's talk. Our presenter is none other than Professor Irena Creed. I've been blessed to have a lot of beautiful professors coming to Science Talk. So this is again one of them, Professor Irena Creed. She is an adjunct professor in ecosystem sciences at UNU-INWEH and professor of environmental sciences at University of Toronto, Canada. Her research focuses on intricate connections between hydrology, biogeochemistry, and ecosystems health. She investigates how water, as it moves through terrestrial and aquatic ecosystems, shapes ecological processes, particularly in the context of global environmental changes and atmospheric pollution. Our work spans multiple scales, from local landscapes to large river basins, with studies in Africa, Asia, Europe, and North America. Our work is also highly applied, with partnerships involving government and industry to develop policy and management tools for sustainable ecosystem practices. She has authored over 200 peer-reviewed publications and delivered more than 100 invited talks. So we are blessed to have in our midst, sharing our insights with us, Professor Irena Creed. So, Irena, welcome.
Thank you so much for that wonderful introduction, Grace, and welcome to everybody on the call. I'd like to start by acknowledging the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful for the opportunity to work on this land. I'm really delighted to be able to speak to you on a project that has really become a major part of my research program over the last decade, as we all are interested in combating climate change. Many of us are familiar with this iconic image. In fact, it is the iconic image for climate science, what we call the hockey stick figure, where we see that over the last 100 years, the temperatures have been increasing at an alarming rate. Yet many people look at this and maybe not appreciate this. I want to give a shout out to young people who are actually being able to communicate sometimes more effectively what is happening to our planet. In this case, Jill Pelto, who's an artist and science communicator from Richland, Washington in the United States, introduces a new kind of art that's informed by scientific data and inspired by early 20th century explorers. This is one of many of her pieces of art, which I found so beautiful, but also informative. If you look very closely to each of the lines, you will see the data points that are underpinning it. But what we see and what we now can feel through the art form are the fact that our glaciers are melting, our sea levels are rising, the temperatures are increasing, and the impact and the consumption of fossil fuels continues to escalate. one of the impacts of this recent change in our climate system are risks for the entire planet. And so this is something that came in the New York Times, and it just shows you that none of us are going to be protected from climate risks, whether it's flooding, heat stress, water stress, wildfires, hurricanes and typhoons, or sea level rise. The entire planet is experiencing these climate risks. Countries have come together to respond to this, and the Paris Agreement is the legally binding international treaty on climate change. As you all know, it was adopted by 196 parties at the UN COP meeting in Paris, France in 2015, and it came into effect in 2016. Now, this agreement sets the goal of a global mean temperature increase of 1.5 degrees Celsius by a rise by 2100. And based on the knowledge that we have now, we're currently sitting as of December 2023 at about 1.3 degrees warming in 2023. That doesn't give us very much room to meet the Paris Agreement goal. And in fact, if we were to look at our current policies and actions, we're actually heading for a 2.7 degree warming, as you can see in the plot over here. The most optimistic scenario is one where we fully implement all of the announced targets that we have made, and that makes us sit at a 1.8 degree warming. Now, as we want to track our progress towards achieving these climate targets, there has been various metrics adopted, and one of them is called the Climate Change Performance Index. And so when we look at this, we'll see the ranking of various nations around the world. And interestingly enough, Denmark is at the top of the rank. And if we look where Canada sits, it sits at 62. And Saudi Arabia, as an example, sits at 67. So we all have work to do, but some countries have more work to do than others. I now want to talk to you about natural climate solutions, which can be a very important tool in mitigating climate change in the near term, and in particular during this climate critical window. Natural climate solutions are actions to protect, conserve, and restore nature in order to store carbon and reduce greenhouse gas emissions. And while this is intuitive and it seems like a very something that many nation states are embracing, there's still yet a lot of confusion and controversy about what actually constitutes a natural climate solution. And because of that, it is actually causing delays in critical climate action. Very recently, a group led by Ellis talked about trying to reduce the confusion and bring clarity. He introduced the principles of natural climate solutions. These are foundational principles that are provided on the outer rim of this circle, and they include obviously nature-based, sustainable, additional, equitable, but also measurable. And I'll be focusing a lot of my presentation today as a scientist on things that are measurable. And under measurable, we need to avoid double counting, report uncertainty, account conservatively, and use the CO2 carbon dioxide equivalent metric. So there is belief by scientists that nature could pull 10 gigatons, and that is equivalent to 10 billion metric tons of carbon from the atmosphere. That amount of carbon represents more than a third of the greenhouse gas emission reductions needed by 2030 to keep the global temperature increases under 2 degrees Celsius. This includes about 5 gigatons that is under the protection of intact lands. And so this is what we would call avoided emissions, so protecting the lands that are currently there. It also includes 5 gigatons in enhanced sinks. And these are areas where we're actually managing our working lands differently or restoring natural cover to create carbon sinks. Now, we know that natural climate solutions can involve a number of different ecosystems, including forests, wetlands, and grasslands, and my focus today will be on wetlands. So, first of all, and it seems like a very innocent question, what is a wetland? May be simple and innocent to ask, but it's actually a very complicated answer. If you were to go to the Oxford Dictionary, you would say they would tell you that wetlands are areas of land where water covers the soil all year or just at certain times of the year. Yet, when we go to the International Panel on Climate Change, it provides definitions of wetlands, but it encourages each country to adopt their own definitions based on specific circumstances. Just to give you an example of some of the complexity of a wetland definition in Canada, I've shown you the cartoon on the left and some results from Google Earth on the right. And we all know the open water center part of the wetland. Surrounding that is emergent vegetation. Surrounding that is what we call a wet meadow zone, and then finally a riparian area. The question then becomes, what is the wetland? Is it only the open water part, or is it the entirety of the emergent and wet meadow zone, or does it even go further to include the riparian area? Why does this matter? When we want to look at the carbon that becomes sequestered and we need to come up with scientific and reproducible results, we need to all be counting the same parts of that ecosystem. Right now, there's still debate in Canada about what if all of these components should indeed be captured. One of the exciting things in the times that we live is the emerging technologies that can allow us to map these different features of open water, emergent, wet meadow, and riparian area from space at various spatial and temporal resolutions. There are many different satellites right now available. Many of them provide data at no cost or little cost, and really is empowering nations to be able to map their wetland inventories. So that could tell you not only what is present, but it could also tell you the dynamics of those wetlands. A lot of the work that we're doing is looking at the contraction and expansion of open water systems and trying to figure out how they too that information can be used to predict the carbon sequestration potential. On the left-hand side, you see a base map, again from space. We can use remote sensing to map the inundated areas. And as you go further right, you'll see that we can capture water or inundated areas in a dry year versus a wet year. We can overlay them. And then to the far right, you'll see that we can actually map the probability of inundation. And this type of information will get us closer to being able to generate both precise and accurate estimates of the carbon sequestration potential, but also the greenhouse gas emission potential. So now that I've described to you what is a wetland, I want to talk to you about how do wetlands actually get recognized in national greenhouse gas inventory reports. Every nation that has signed the Paris Agreement must submit a national greenhouse gas inventory report each year. Now, that report does not necessarily need to include wetlands. Wetlands must be classified as managed lands in order to be included in national greenhouse gas inventory reports. But in Canada, a country where we have still many wetlands, these wetlands are considered unmanaged, and therefore to date, wetlands are not currently included in the national greenhouse gas inventory reports. Just to give you a contrast to our neighbor to the south, the United States, most wetlands are considered managed, yet still these wetlands are still not included in the national greenhouse gas inventory reports. And in a meeting recently in Washington, D.C., a lot of the limitations for their inclusion is to be able to identify where they are and to be able to quantify their carbon source or sink potential. But we definitely feel that there is a move both in Canada and the US that we're now having enough information that we can actually incorporate wetlands, classify them as managed, and incorporate them in our national greenhouse gas inventory reports. In this work of trying to decide and working on behalf of the Government of Canada, we were asked to survey wetland experts to determine if we could come up with criteria, indicators, and thresholds to actually classify a wetland as managed. And I'm just going to share with you 4 of some of the findings that we had. And the first one, which is interesting because it shows you the importance of language, managed, at least initially, for inclusion, it kind of captures the negative impacts that humans are having on wetlands. And yet, managed could be done in a very positive way, that many not-for-profit groups and other government agencies are actually actively managing wetlands to sequester more carbon and reduce greenhouse gas emissions. So we wanted to acknowledge there's bias in the term of a wetland being managed. Secondly, human activity must be considered within not only the wetland itself, but the entire contributing catchment area to that wetland and also to its downstream waters. Third, the type, magnitude, and intensity of human activity must be considered. Right now, it's a binary. It is managed or it's not managed. And yet, when you think about landscapes in your countries, and in Canada, we can have very different intensities of management. Ones that are very passive or low human activity on certain grasslands to ones that are heavily managed, for example, with intensive commercial agriculture. And so we think that we need to kind of go a bit deeper and not just talk about managed, unmanaged, but consider the type, magnitude, and intensity of human activity. And finally, number 4, that recognizing that we have mitigation measures to the impacts of the surrounding land through things like riparian buffers that should also be acknowledged. Just this one example, it's exciting data that is coming, is currently under review, but was generated by some of members of our national research network on wetlands as natural climate solutions. This is led under the leadership of Matt Bocard from Lethbridge University. And he's showing data here with cropland versus perennial or grassland to the right. And obviously the nitrous oxide is very low in this landscape. That's why you don't see the gray bar. But what you see is that wetlands that are surrounded by croplands have much more methane being produced than perennial grasslands. In this case, the CO2 was more or less equivalent against both land uses. And so what's really important here is to say wetland is not a wetland. You can't treat it similarly, even within a similar geographic area, but we must understand the type, magnitude, and nature of human activity surrounding it in order to predict what the greenhouse gas emissions as well as carbon sinks could be. So we're proposing to the federal government that we need a decision tree to determine if a wetland is managed based on what the IPCC calls a land proxy approach. And I've covered what comes directly as recommendations from the IPCC in black and where are the innovations of what we're suggesting in the highlighted color and the yellow. So from the left, the IPCC would say, is the hydrology managed, altered, or enhanced, either up gradient of the wetland or within the wetland itself? And if it is, it's considered managed. If it's not, the next question is the wetland within, the vegetation within the wetland managed? If it is, it's managed. If it not, it goes to the next question. And these are the ones that refer to what I was just saying. Is the wetland situated in a landscape where human activities exceed a threshold in human activity? And so, if the human activities, let me clarify that. If there's a threshold of human activity above which you're going to have changes in the carbon flows, and if the answer is yes, were human mitigative measures introduced? And if the answer is no, then we can consider that land managed. And so right now we're working with research scientists, both from the government and within our network, to see what the implication of this would be for inclusion of wetlands within our own national greenhouse gas inventory report. One of the biggest challenges, though, and this was definitely discussed at the Washington, D.C. meeting, was how do we avoid double accounting for carbon? If we have carbon in the upslope, in the wetland, and downslope, who gets credit for sequestering it, and who gets the penalty, so to speak, for allowing it to go down to the next ecosystem? Seems like a pretty basic question, but these are the types of, we need answers to those questions if we're going to be empowering the use of nature as natural climate solutions. The third question is how should we report on wetlands in terms of global warming potential? Remember that I said that one of the principles was that we should be able to use it into the terms of CO2 equivalents. And I just want to talk a little bit about that now. In this image, again, taken from Sweden, we know that wetlands are carbon reactors. They're really good at storing nutrients and carbon, but they're also good at emitting them. And there's major attention right now on the role of wetlands in greenhouse gas emissions. In fact, this one from the UNU-INWEH, which was published in August of this year, talks about the concern of rising methane emissions from wetlands that might undermine our climate targets. In fact, the concern about methanes coming from nature occurs not only for wetlands, but many of the other natural ecosystems as well. I would consider it one of the hottest areas of research in our field at this point in time. So why is methane a concern? Well, this is just basic from the IPCC account of the different power of different greenhouse gases in terms of their warming potential. If you look at one molecule of CO2 and compare its global warming potential power to methane, methane is 28 to 36 more powerful, and nitrous oxide an order of magnitude even more than that. So definitely each greenhouse gas has a different global warming potential. The other thing is, and it's really important to consider when we look at this issue of methane, is the lifetime of the gas in the atmosphere. CO2 is in the atmosphere in the order of thousands of years, but methane is only in the atmosphere for about 10 years. And yet the way it's currently done, they're measured over the same time period. And so in some regards, we need to be careful as scientists to ensure that we're really capturing the behavior of the methane gas, not only its potency as a greenhouse gas, but also the short time period that it's in its atmosphere, if we're going to effectively capture its role in climate mitigation. So this is a bit of a busy slide, but I felt it was important enough to be able to put it in this slide deck and share it with you. Right now, the metric that's used for many of the greenhouse gas accounting is called the global warming potential, the GWP. The definition of this, it's the amount of energy 1 ton of a gas absorbs in the atmosphere relative to CO2 over a specific period of time. The pros of this approach is that it's easy to implement and it's standard for expressing CO2 equivalent emissions. The cons is that it de-emphasizes the effect of short-lived gases such as methane. A relatively new metric that was recently introduced was the global warming potential star. And this is the amount of energy a step change emission of a gas absorbs in the atmosphere. And here I want you to think about that step change being potentially resulting from the rewetting of a wetland or the loss of a wetland relative to a pulse emission of CO2 over a specific period of time. The pros is that this is a much more accurate representation because it compares a step change of a short-lived gas to a pulse of CO2, and it's designed to be easily implementable into current policy. The cons are it relies on GWP values to calculate the effect of the step emissions, and it's applicable only for short-lived gases. Other metrics are needed for the longer-term ones. So we decided to look further at comparing what if, for example, IPCC were to shift and use GWP star, especially when considering natural climate solutions of wetlands. So we know that with the wetland carbon cycle, it's kind of like a tug of war. We have CO2 that's sequestered into the wetland. At the same time, we can have methane emitted from that wetland. And with the methane being short-lived and more powerful global warming potential, that's where a lot of the concerns are and basically concerns that are leading to inaction in terms of using wetlands as natural climate solutions. So we wanted to synthesize the available literature and find out, well, where's the evidence for that? One of the PhD students in my group, Shiju Ma, recently compiled the literature for CO2 and methane flux rates from inland wetlands throughout North America. The first thing I want to point out is we don't have a lot of data that on these greenhouse gas emissions. And in fact, while this one focuses on inland wetlands and there's additional data available for example, tidal or coastal wetlands, there isn't a lot of data that we have to make these scientific judgments. Yet, I want to show that on the top right, you'll see what the CO2 fluxes are, and I do it for both a natural or an intact wetland, a drained wetland, and a restored wetland. And then on the x-axis, you see the CO2 flux rate. And what you will see is if we keep wetlands intact in their natural condition, they are sinks of carbon. If we drain them in terms of CO2, if we drain them, you're getting major CO2 emissions. But if we restore them, we can actually not only achieve what they were when they were intact, but even greater carbon sequestration potential. So the CO2 story is relatively straightforward. But if we go to the methane one, and that's the plot on the bottom, and the methane flux, again, from 0 to 600, and the intact drain and restored on the y-axis, you'll see that in general, most of the wetlands had relatively low emission rates, whether they were intact, drained, or restored. The orange colored ones represent really high methane emitting wetlands. Of course, we don't want to treat these as outliers. We want to understand which conditions wetlands produce these high levels of methane, and that's an avenue for future research. What we then did was we looked at using model simulations to look at three different scenarios. One is we have the wetland and we keep it intact. One is we have the wetland and we drain it. And the third one is we drain a wetland and then we restore, or also called re-wetting the wetland. And in the red line, you'll see the global warming potential star. So that's that new metric. And in the blue line, in the green line, let me correct myself. The red and the green represent high and low methane emissions. And on the left and the right, you'll see the global warming potential star compared to what is traditionally used. And so clearly, when we look at the controversy, as is often the case when there is something controversial, depending upon where you are, wetlands can be bad in terms of a natural climate solution because they do generate methane in some cases. However, when we look at the low emitting one, which represents the majority of the wetlands, we can see that it's a sink status. So when you see the green line go below that horizontal line, that means it's sequestering carbon. That's the case for when it's intact. That is, you see that it actually, when you drain them, you're going to get an increase of the global warming potential. And then when you re-wet them, you might get an initial increase, but a long-term benefit. Now, this scenario analysis tells us that natural climate solutions are not as quick in terms of providing the mitigation. It is a long-term investment. And in this case, with re-wetting, we're talking about the span of 100 years in terms of time needed before we start seeing those benefits. And so that doesn't mean we shouldn't do it, but we also have to look at other measures in the interim to meet the shorter-term Paris Agreement commitments. So now I want to go on to the fourth question, which is how can we estimate carbon sequestration potential in protected and the restored wetlands? So when we look at wetland protection, we can see that protecting wetlands avoids the release of greenhouse gases, but have we actually measured the carbon sequestration potential of these intact wetlands? So we've been funded by the federal government to look at wetlands across the agricultural zones of Canada to actually quantify how much carbon is being sequestered. And here in the next slide is some of the results. These involve those inland wetlands all the way from Alberta to Ontario, and it shows you that the organic carbon sequestration rate can be relatively variable. It's not a normal distribution. It can go from levels as low as 0.2 megagrams carbon per hectare per year up to 1.6. And our range is actually relatively lower compared to reports from the United States. In a recent meeting at the Washington, D.C., the members of the US were showing that their rates are actually a bit higher. So they're geographically variable. Now, as a policymaker, you want to be able, and to implement policies, you need to be able to have measurable results and be able to predict how much carbon will be sequestered. And so we brought together kind of a thought experiment based on expert opinion together with the scientific literature to be able to look at what are the state factors, the interactive controls, the indirect controls, and direct controls on the wetland carbon cycle. The state factors include things like climate, geology, topography, biology, and time. And when we go to the direct controls, they include the carbon quantity, the carbon quality, bulk density, cation exchange capacity, aggregate reactivity, redox potential, or oxygen availability, and temperature. Now, this is pretty complex. And how do we go about measuring wetlands, individual wetlands, to predict their carbon sequestration potential given this complexity? Well, we wanted to see and explore what we could do through using satellite remote sensing. And so I'm going to share those results with you in a moment, but we looked at things like the Integrated Normalized Difference Vegetation Index, what we call the INDVI, the inundation probability, and the land surface temperature. So we're trying to find some of those direct controls that could be remotely sensed. But this kind of figure is a classic, and from almost 100 years now, Jenny wrote the Bible on soil forming processes. But since then, we've had the Anthropocene. And so we have a lot of effects of human activity on those direct controls. And so here we wanted to see what we can remotely sense in terms of a human impact index and to determine how that as well would influence the wetland carbon cycle. Now, you can see something about these complex systems here. And one of the things, and I know the rector of the UNU is quite passionate about, is the use of artificial intelligence. And so we can use artificial intelligence to aid in the prediction of these wetland carbon sequestration rates. We decided to do a project and see how much we could explain. We took those satellite sensible direct controls, we put them into a correlation matrix and tried to reduce the number of variables by removing those that were correlated with each other. And then we put them into a random forest, one of the machine learning techniques. And you'll see here at the top, RF is the random forest model. These are the various attributes that we included, the remotely sensed ones of human impact, normalized difference vegetation index, the inundation probability, and land surface temperature. But we also know the importance of soil. And so we used national scale, relatively coarse soil property maps in these models as well. And what we're really pleased to report is that we were able to use the machine learning technique to come up with models that have a correlation coefficient of 92%, very close slope to the one-to-one line, highly significant results. So what does that mean? It means that it empowers us to be able to, as a country who wants to include wetlands, managed wetlands and national greenhouse gas inventory reports, that we can now estimate what those sequestration rates are. Some of you who know machine learning will know that there's two kind of outputs that it can generate. One for the random forest, one of them is a variable importance plot, and the other one are the partial dependencies. The variable importance plot is the one on the left, and we can see that the number one influencer on the carbon sequestration rate was indeed the human impact index. After that, it was the soil properties, and then below that, you'll see the inundation probability and the productivity measured by the normalized difference vegetation index were also important. Interestingly enough, the least important was the land surface temperature. It's really nice to kind of open the hood on the machine, so to speak, and understand how it sees the correlations of these various direct controls with carbon sequestration so that we can, ensure that we can explain it mechanistically, that we have a process-based understanding of what some of these patterns will be. And so I showed you one that had all the variables at the top. And so that's the performance of the model there. I then wanted to test what happens if we want to do less work and include less variables. And so from the top, it had all in, and then you can see I systematically reduced a variable as I went down each row. And you can see that we can still generate relatively good predictions for wetland carbon sequestration rate if we just use the human impact index and the inundation probability. And here you can see an adjusted R-squared of 82% and a slope of 82, which we feel are actually not just reasonable. We're actually pretty excited about those results and eager to share them with decision makers. So that's the protection piece, but we also want to now look at the wetland restoration piece. And restoration turns degraded or drained wetlands from carbon sources to sinks. But how can we then estimate the carbon sequestration potential in these restored wetlands? Well, I told you that the intact ones, the data was pretty sparse. I could share with you that the wetland restoration data is even sparser. And yet there are many initiatives, especially in the Northern Hemisphere that I'm aware of, that are starting to collect these data. First of all, let's look at what the wetland restoration potential might be. An exciting recent paper that was published in Nature talked about the global wetland loss over the past 300 centuries. And I wanted to include this figure for you all because I wanted you especially to understand the drivers of wetland loss in the Northern Hemisphere. And here you can see, especially in Fennoscandia and parts of Europe, that forestry was the main driver of wetland loss. If we look into the United States, agricultural drainage is the major source of wetland loss. And if you look in the South, you can see that many wetlands are still protected, especially in the Amazon and the Congo. But where we do see losses in Asia and sub-Saharan Africa, it's typically related to agriculture, the need for food. So now we can see where wetlands were and where also they can potentially be restored. In some talks, I refer to them as the ghost wetlands, and the idea that we can resurrect some of these wetlands through restoration practices. Now, many countries, especially to my knowledge in the North, I can't speak so much for the South, but I'd love to learn from anybody who is aware of that, but they're investing a lot of money into restoring these wetlands. I want to share with you what Canada is doing. Canada's investments in natural climate solutions are supported under Bill C-12, where it states that it supports Canada's efforts to achieve net zero greenhouse gas emissions by the year 2050. And it made 10-year fiscal commitments starting in 2022 that included $3.2 billion for the planting of 2 billion trees initiative, $631 million to protect and restore grasslands and wetlands, and additional $98 million to establish a new natural climate solutions for agriculture fund. So a lot of money is going to boots on the ground efforts to restore wetlands. But how much do we really know about the climate benefits of the restored wetlands? One of my colleagues in Sweden, when there was a lot of similar attention as in Canada, in Sweden about natural climate solutions and the rewetting, comes from my colleague Hjalmar Loudon from SLU in Umeå, Sweden. And he's one of the part of the consortium of scientists who are actively collecting data and measuring these greenhouse gas fluxes from wetlands in Sweden. And his comment is, I'm amazed at how little we actually know about restoring wetlands and the benefits that that might be for natural climate solutions. In Canada, and this is where you will see that I've been working on this for well over a decade at this point, we established a chronosequence of restored wetlands, both in Alberta and in Ontario, to monitor changes in the rates of carbon sequestration with restoration age. So these are from, some of you may know Cambridge, Ontario, and they have the Tim Hortons camp. And these are the wetlands that have been restored by Ducks Unlimited Canada on their property. And in that relatively small geographic area, we had drained wetlands, wetlands that were drained 15 years ago, 25 years ago, 45, no, sorry, that were restored 15 years ago, 25 years ago, 40 years ago, and those that were intact. And just in case you wonder if I ever get out in the field, it is I, along with my wonderful colleague Erica Nunga from Kenya, who are in the kayak doing the sampling. What we wanted to do here was to look at easy to restore wetlands that are relatively small, have no hydrologic inflow or outflow, and are drained simply by plugging the drainage ditch that was used to drain them. So this would be in support of cheap, easy to restore wetlands, and we wanted to see what the climate benefits would be. We used lead and cesium radioisotope dating to estimate the annual organic carbon sequestration rates along that chronosequence. And this data has not yet been published, so you're one of the first audiences to see it. And here we see that chronosequence, and this includes data all the way from Alberta to Ontario on those restoration ages from 0 to 40 years and the total organic carbon stock that is accumulated. So yes, re-wetting wetlands will sequester carbon and increase the removal of carbon from the atmosphere. But we also wanted to look at the change in organic carbon, not just the accumulation. So in this case, you'll see the restoration age, and you see the change in organic carbon stock, and we see this kind of nonlinear response. And what we recognize is that when you first restore it in the years about 0 to 5 to 10 years, you're getting a big increase in the carbon sequestration rate. And then after about 10 years, the change in rate starts to decline. And then after about 20 years, you're back to what it would have been in a natural ecosystem. And so right now we're exploring what could be some of the mechanisms that drive the increase and the rate of that increase, and in turn, the decrease following that 10 years. And some of the ideas that we're coming up with is that intact wetlands are typically, except if they're heavily impacted by surrounding croplands, nutrient limited. And so they will have a relatively lower carbon accumulation stock. But if you drain them, they become water limited. And we saw the evidence that they become pumps of CO2 after that. And so you still have a low carbon accumulation in the drain ones. In the early restored ones, we're releasing the nutrient and the water limitations, and therefore we're getting these rapid increases in the carbon stock. But eventually the nutrients start to become limiting, and then you get a decrease in that carbon stock until you reach that new equilibrium after 20 years. What this type of evidence empowers us to do is to think about how we can use human intelligence to prolong the carbon accumulation to the peak, increase the peak, and also lengthen the amount of time of the increased rate of carbon accumulation. And so my PhD student and I are just about to submit a paper to Wetlands where we talk about various management interventions that can be done to help manipulate the carbon cycle. The last piece of the science that I want to talk to you about is modeling the carbon benefits of wetlands. How can we predict change in carbon status as wetlands go from intact to drained to restored? And one of the new research areas that we're working on, and again, this one's in Sweden, in Vindeln and Skotgård, but we also are going to be doing this in parts of Canada where we've set up flux towers and are starting to collect new data, is to simulate when wetlands go from intact to drained to restored, what happens to their carbon state, And we want to do that not only for individual wetlands, but for wetlandscapes. And we know that wetlands interact with each other, but we also know that carbon can flow into them, but they also can flow out of them. And so we want to build models of the carbon flows across landscapes. Exciting work that's just starting, and we'll look forward to sharing those results with you at a future time. Finally, I want to talk about the economics of this. And with knowledge of the carbon sequestration rates, the question then becomes, how can we incentivize both the protection and the restoration of wetlands? So my colleagues who are in sociology and economics joined forces with us to explore what the carbon market potential could be. And so using the data that we pulled together from Canada's agricultural landscapes, we used the mean carbon sequestration rate. We selected a 30-year time frame from 21 to 2050. We chose 2050 because Canada's committed to net zero emissions by 2050, and we wanted to see how much of this incentivization could benefit Canada. We also looked at the cost of restoring wetlands, and we took an average value that it cost from Ducks Unlimited, shared this information with us, that is about $31,000 per hectare. And then finally, we calculated the benefit to cost ratio. Now, if the ratio is equal to 1, you break even in terms of the benefits and costs. And the benefits are from the carbon lens only, and the costs are everything above of restoring that wetland. If the ratio is greater than 1, then the wetland restoration project is justified based on carbon benefits. So let's look and see what we can predict from the benefit to cost ratio for our wetlands. Once again, our climate target 2050, period of 30 years, and you can read the table, but I want to emphasize what the key findings were. Number one is it's better to protect than to restore wetlands based on carbon sequestration potential. You'll see that the benefit to cost ratio is above 1. It's 1.23 for protection. That's a good thing. And it's well below 1 for restoration, which means it's not economically viable to have to incentivize through carbon market the restoring of wetlands based on carbon alone. And so the key takeaway from that is we must incentivize landowners to maintain the remaining intact wetlands on their landscapes. But the other point is this has been a very carbon-focused talk for the reason of natural climate solutions. But there are many other benefits that wetlands can provide, many other ecosystem benefits that include water purification, flood drought mitigation, biodiversity. And so we need to include those to incentivize wetland restoration. So the second major finding is carbon benefits alone, at least not today, are enough to incentivize the restoration of wetlands. Yet, if we brought in the biodiversity, the flood drought mitigation, the water purification, it will likely definitely be incentives to restore wetlands. So now that we've entered in that it can't just be carbon alone, we need to explore the synergies and conflicts between wetlands as natural solutions for carbon versus other societal challenges like the tremendous loss of biodiversity. Wetlands provide more ecosystems services than carbon, and yet we are not in the position to be able to easily quantify that. And so I just wanted to share with you some of the work that I'm doing internationally and led by my wonderful colleague Karin Eklof from Sweden. And we're doing a major meta-analysis trying to gather that data. So identifying wetland studies, selecting them in terms of their various attributes from greenhouse gas, hydrology, mercury, biodiversity, pests, nutrients, recreation, and infectious diseases. And so through that process, we hope to be able to contribute to decision-making in 3 ways. One of them is an opinion paper on the role of wetland restoration for planetary health. One is a synthesis paper, which will look at the long-term evaluation of wetland restoration and its effects on hydrology, biodiversity, water quality, and greenhouse gas balance. And the third, which we really want to take the theory and be able to apply it to practice, is in a handbook that is being led. I'm one of the co-editors on of terrestrial ecohydrology on inland wetlands as nature-based solutions. And so I just wanted to put a call out there for anybody interested in building a global evidence base for wetlands as natural climate solutions to reach out to me. I think that there is great potential to be able to contribute to global assessment reports or high impact papers that cover not only the North, which is where a lot of my activities have been, but also in the South. There's incredible work that is being done on the continent of Africa, for example, using the new remote sensing that detects methane emissions. And there's so much more that we can learn by working closer together. And so on that invitation, I just wanted to thank you for the opportunity of speaking to you today, and I look forward to any questions that you might have.
Thank you. Wow. That's quite a class, I must say. It's a lot of information to process, but very quickly, let me say thank you very much for what you do and the time and the effort in sharing this aspect, you know, on the role of wetlands, carbon sequestration, and climate change and all that with us. But very quickly, taking you back to the basics, actually, very, very rudimentary. So bottom line, the issue of wetlands is not so much in the hands of the individuals or the masses. It's pretty much resides with what I'll say the government, the institution. Correct me if I'm wrong, true or false?
So is the question, sorry, could you repeat that, Grace? That the issue of wetlands.
Yeah, that when you talk about wetlands in the way it was defined, either from the Webster Dictionary or the IPCC, the way you have traced it, you know, pretty much the management of it, the delineation of it really resides with the government and not so much with the people, true or false?
I would say that it depends on the context. As scientists, we can define a wetland very readily. To be able to map it and create a wetland inventory, we rely on scientific tools. Those tools can capture different components of the wetland. And depending upon what governments decide to use in their wetland inventories based on the availability of the data, they may choose to take only part of the wetland or the entirety of it. So what we're finding is there's no consistent definition. And just to give you a further example, even in Canada, we define wetlands as features that have water depth of less than 2 meters. In the United States, they define wetlands as less than 4 meters. So even our closest neighbor doesn't have the same definition of what a wetland is. And my argument is that if we don't come up with a consensus of what a wetland is, how can we then create an inventory that could then be used within some of the national greenhouse gas inventory reports or as a basis for natural climate solutions?
Thank you for that clarification, but I'm still interested in this basics. So at the end of the day, regardless of the definition, the management, the management of wetlands still resides with a formal institution, not so much in the hands of individuals.
Well, again, the answer would be yes, because wetland is regulated under provincial and federal laws, and therefore there's restrictions as to what individuals can do. However, the practice is that there is a lot of degradation and drainage of wetlands that is ongoing, And so even though it may not be an official voice, I think the people have a lot of power in determining the fate of these wetlands on our landscape.
Oh, okay. I'll come back to that. Satya is asking, well, it's a great presentation, so kudos to you. And they've been able to learn a lot, like myself too. But the question is, could you please share your thoughts on whether the thawing of permafrost might be contributing to the recent increase in methane emissions?
So much of my work is not on the peat-dominated landscapes of the Northern Hemisphere, but I can give you my opinion that's not based on my expertise, that the answer is absolutely yes. With the thawing of the methane, the warming of the landscape, if you think about those systems approach and all the direct controls that influence carbon cycling rate, there's going to be a lot more dissolved organic carbon. There's going to be much more, we're exploring whether it's more labile, bioavailable carbon that's being released by the melting permafrost. So you'll have a lot more substrate there that in turn can be processed by microorganisms to produce methane gas. And so a very high likelihood that we're going to get major methane effluxes coming in the form of the thaw due to the thawing of the permafrost. Absolutely, Satya.
Okay, all right. Then Taha also joined in by saying again, thank you. But the question is, what is the difference between natural climate solutions and nature-based solutions? Why the difference in terminology?
Well, I think another really great question, and I'm going to be very transparent with you. In a recent paper that we submitted, we talked about nature-based solutions, and there's also nature-based climate solutions, and then there's natural climate solutions. And then there's another term that is being floated out there right now. And they each mean something different. And so from natural climate solutions, it's really looking at it from that climate change, atmospheric gas mitigation potential. Nature-based solutions would be much more inclusive of the flood drought mitigation, the biodiversity, the water purification, and other solutions that address societal challenges. So it's a much more broader and inclusive of the various services that wetlands can provide.
Okay, before throwing it open to my colleagues there, I still want to ask this question. Coming back to the findings now, one of the major findings, or the first one actually, is it's better to protect than restore wetlands. Is that really realistic? Do we really have a lot of protected wetlands? Do we really have a lot of, space and incentive to keep wetlands intact?
Well, your question is one of public will. Right now, we have intact wetlands on the land. And the question, but we also have growing pressures for housing, for food, for energy. And so the question is, we need to make the case that wetlands are value, nature has value. To pick up on my title, we need to invest in nature because the benefits that nature provides is sometimes not quantified and therefore not recognized. And so I would say that absolutely we have that ability. We need to have the political will to do that.
Political will, that would be well said, for governments. But I also know in many developing nations, there's a lot of, a struggle bottom up, when people really wanted land for residents and all that. They're really encroaching on wetlands, even when government is trying to, create buffers and saying, no, this is a no-touch area. But there's a strong push from the people. We need houses, or we even need for agricultural purposes, and from what you are saying, this is really not good.
No, what I'm saying is that we're not as smart as nature to create wetlands with the services that they produce. But what I'm also saying is we need to recognize them. And so in my recent trip to Uganda, where I have been working for some time, I had the privilege of being able to drive through landscapes of papyrus swamps and the vast amount of papyrus swamps that exist there. They are under enormous pressure because people need space to grow food. And so the question is, how do governments make decision between keeping a resource that might be remarkable for a climate solution versus feeding people? And at the root of that is the whole piece that I wanted to focus on is how do you incentivize that change in behavior?
Yeah.
And to me, it's about equity. To me, it's about access. To me, it's about payment for those services. And so if you protect or restore a wetland, which means that you take away other food or other options, that there's a financial transaction involved and you pay the communities that are the caretakers of those wetlands, so that enables them to pursue other sources for food, as an example.
Okay, quickly, one question also came in from Ratnajit. I hope I got that correctly. It's saying wetland is considered one of the major potential active options of carbon sink. Now, is there any established mechanisms how wetlands are keeping more carbon compared to other land uses?
If I were to share with you, Ratnajit, that systems diagram of what controls carbon going into the wetland, you will see that it depends on it having a carbon source. And if you imagine, wetlands are often at the bottom of a lot of hydrology that drains into them, so they might have a lot of carbon captured in there. They have typically low oxygen conditions, which means there's not a lot of decomposition of that carbon, so that gives it an opportunity to accumulate. So those two pieces right there mean that, and especially because they're locked in water, underneath water, that they can store that much more carbon. Now, I'm not sure I would say more than forests, because that's also another natural climate solution, and you can imagine how much carbon is locked into growing trees. And now we're looking even at the oceans and what can be stored in oceans, although that's a topic for another day and by another scientist. But wetlands, despite being really small, are disproportionately important in the carbon landscape. And so it's essentially, you got water, low oxygen, carbon accumulates. And that happens not only in the peatlands in the north, but also on the more working landscapes in southern areas.
It's okay. Any question from the audience?
Please. You're over time. Yeah, that's fine.
Okay.
Just, I mean, we are over time, so I won't have the chance to ask questions, but I wanted to thank you really for a wonderful presentation. Really, really wonderful. And it's, you know, it's a kind of a coincidence, or, you know, good thing that what you're presenting is very much in line with the report that we are now putting together for the COP, UNCCD COP, coming up in December, and a big delegation from UNU would be there. Discussion is all about essentially the economics of drought resilience, why investing in nature would pay off. You know, what are the costs and benefits? And for me, those comparisons were very helpful. And you know, we are trying to engage and encourage many governments around the world to appreciate the value of these sorts of investments and protection. Yet, you know, it's very hard to be convincing, and we need more research and more solid work like yours to provide the proof, not only in this country but in other parts of the world, that more investments are needed. It is possible to convince people. It is possible to also attach, you know, other maybe measurable, I would say, you know, contributions in terms of creating stability. You know, the contributions that wetlands are making to rural populations, creating employment opportunities, sustainable modes of livelihoods, and so on, which are of extreme value in the current situation of the world. We have wars and migrations and a lot of catastrophic events around the world. So just congratulations to you, and it's so wonderful to have you with us as one of the team members who's leading a great work. Thank you.
Well, thank you so much, Kaveh. And I just want to say that I represent a consortium of almost 50 scientists, both in Canada and in Europe. And it's because of them that I can share what I did today. But I also want to share with you, and it speaks to Grace's comment about incentives and opportunities for those who are most at risk. One of the things that we really want to do is to explore more deeply the carbon markets, especially for Indigenous communities in Canada. And I would think, Grace, it would also be relevant to rural and remote communities in the Southern Hemisphere. And how do we make them, and this addresses Shira's question about engaging the stakeholders, the end users, the beneficiaries into the discussion about how we can create those carbon markets so that those who are most vulnerable can benefit and uplift themselves through engaging in a natural climate solution. And so that's just at the leading edge. I think there's quite a great promise both in Canada's communities but internationally as well, that I hope that we can continue the conversation and move that forward in the future.
It's all right. I guess it's a safe place to call it a wrap. Thank you so much. Irena, we appreciate your insight, the time, the effort. And for everyone who has taken time to join us today, I believe you can tell that this is yet another informative science talk. So hopefully you'll join us next week. Once again, on behalf of everyone, Professor Irena Creed, thank you for your presentation.
Thank you all.